define the decay constant of a radioactive nuclide. So the decay constant, we use the symbol lambda, is the probability of a decay per unit time. So it's one of your definitions you need to know. Now the formula that we have for radioactivity are these over here, and you need to know what each of those symbols obviously stands for. So we have in B1, plutonium-239 has a half-life of 2.4 times 10 to the 4 years. Show that the decay constant of plutonium-239 is approximately 3 times 10 to the negative 5 years. So we would obviously use this formula over here because we have our half-life and we want to work out that. So our lambda is going to be the ln of 2 divided by 2.4 times 10 to the 4. We'll put that into our calculator. Just get my calculator here. So we're going to get ln. Now this is the natural log, so it's this button over here, and it's going to be 2, and we're going to divide that by 2.4, and again it's really important that you use this way of writing scientific notation to your calculator, and we get that, and that's equal to 2.88 times 10 to the negative 5. It's actually 2.89 if I was rounding it like that, which is approximately equal to 3 times 10 to the negative 5. And that is obviously going to be year to the negative 1 because we're dividing by year, so year to the negative 1. And it says calculate the time taken for the activity of a freshly prepared sample of plutonium-239 to fall to 0.1% of its initial value. So we're looking at the activity is going to fall to 0.1% of its initial value. So let me bring this back out again here. Now we have with this over here, because this lambda n0, this would be your activity 0, because this is the probability that a nuclide will decay at a specific time, and this is the number of nuclei. So the product of those would give you your activity 0 or at the start. So if I write this as A over A0 is equal to E minus lambda T, we can use that formula. So let me just give some space there. So we have here that the activity has fallen. This is the activity, is that ratio would be 0.1%. Now remember, percent is divided by 100, so we're actually looking at 0.001 is equal to E minus, and we have our lambda here, it's 3 times 10 to the negative 5. We will put that in. I'm going to have to use a bit of log laws here. I'm going to change it away from my exponential form into my log form, and that's going to be the ln of 0.001. I use my natural log because I'm to the e, and I'm going to divide that. That would equal your minus lambda t. So I'm going to divide by my minus lambda, and that will give me t. So I put that in to the calculator. Let's just do that. So we got ln, and it's 0.001, close brackets, divided by, now I'm not going to worry about the minus sign, I'll just see that at the end that it will work, and we are looking at our lambda is 3 exponent negative 5, and we get that. We get, remember this minus obviously doesn't count because we're dividing through by a minus, minus divided by a minus, so we've got 2.230258 points. So I'm going to do it to two significant figures, so it's going to be 2.3 times 10 to the 1, 2, 3, 4, 5 to the 5. That will be the time, 2.3 times 10 to the 5 years, so a long time. Now you could have actually done this another way without doing really with using your formulas, and to do that you could have just calculated, because it's going to 0.1%. So if we start off at 100 at 100%, or and we go down to then it's going to be 100, and we go to 50, that would be 125 would be the next 12.5. Keep on going here, 6.25. Then we can go another one here, about 3, 1.5. I've done a little bit of an approximation there, and you can just keep on going here to that will be 0.75, another one 0.375, another one 0.118, and then this is going to 0.09. So we have got 1 half-life, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 half-lives, and each half-life is 2.4 times 10 to the 4. So it's going to be 10 times that, 10 times 2.4 times 10 to the 4. So we're looking at about 2.4 times 10 to the 5, which gives you pretty roughly the same value. So you could have actually done it like that. They would have accepted one doing it like that.